work that I will present is in collaboration with Gustavo Alexis Dominguez Castro. He's my PhD student at UNAM. And what about this work? So the idea is to address on a long-standing question of non-conventional superconductivity. But to address on this long-standing question, unsolved long-standing question, what we will do, what we did, is to study non-conventional superfluidity. In a few slides, we will see why studying non-conventional superfluidity is equivalent to study the unsolved question of non-conventional superconductivity. And the model that we will use to describe non-conventional superfluidity relies on the use of ultracold dipolar gases. In a moment, I will explain this model, of course. The outline of this talk, first, I will briefly mention to what kind of transition belong the superfluid state first discovered in helium-3 and then in helium-4. Remember that helium-3 is fermion and helium-4 is boson. And then I will talk about the similarities among these two phenomena, that is superconductivity and superfluidity, and why we are trying, with the study of superfluidity, trying to understand the question about non-conventional superconductivity. Of course, I will tell you why it's non-conventional. Then, I will present the model that we are using within the context of quantum simulations of condensed matter. The model consists of a bilayer formed by two optical lattices in which fermions are confined and then traveling in the layers. But to analyze this model, first we concentrate in the two-body problem, and then we will go to the many-body system within the mean field analysis. Finally, I will present a summary of our results. Okay, so as I told you, let me first say a few words about phase transitions. So, the usual phase transitions that we know, phase transitions at finite temperature, are the so-called first order and second order. Which are the main features of first order phase transition? So the main feature perhaps is that the extensive thermodynamic variables as the entropy, the energy, and the density are discontinuous across the transition. Examples of these first order transitions are solid vapor, liquid solid, and liquid vapor, and the triple point. Here I am showing you in Spanish, I'm sorry. the phase diagram of a pure substance in which you can see the different transitions across this line. We have just first order phase transitions. But then there are also second order phase transitions, and they are characterized by having continuous extensive thermodynamic variables across the transition. But in contrast, they have the second derivative of the free energy, for instance, the specific heat or any other susceptibility. They are discontinuous or non-analytic, even more, across the transition. So remember that the second order phase transitions are characterized by an order parameter which is 0 above the transition and different of 0 below the transition, below the transition temperature. Examples of this second order phase transition are, of course, the critical point. Remember that this model, the van der Waals model, and of course the examples that we will deal with in our problem, that is the superconductivity and the superfluidity phenomenon. Let me show you in the next slide what is the line of time of the superconductivity and superfluidity phenomena. First, remember that in 1908, helium-4 was liquefied for the first time, and then in 1911, superconductivity was discovered in a metal by Kamelin Ones at 4.2 degrees Kelvin. Then in red color means experimental discoveries, while black color means theoretical contributions. Remember that the Bose-Einstein condensation prediction was made in 1925 by Bose and Einstein, and then in 1938, the superfluidity in helium-4 was discovered by Piotr Kapitsa, and then Bogoliubov explained this superfluidity, this phenomena, with his theory. I will talk about in a few slides about the Bogoliubov work. But what about the superconductivity phenomenon discovered in a metal at 4.2 degrees? So the first attempt to explain the superconductivity phenomena was done by the Ginzburg-Landau theory in this time, and then the celebrated theory of the Bardeen-Kuperi-Schiffer, mainly based in the understanding of the coupling of the pairing mechanism, was established in 1957, and then later on, Anthony Leggett explained the superfluidity of helium. No, this is an experiment, sorry. In this year, the superfluidity in helium-3, that is the fermion, was reached. In 75, Anthony Leggett explained exactly the superfluidity in helium-3. And I will tell you how he explained. Then, in 86, came a new phenomenon, the high TC superconductivity. Why high TC? Because high TC, in this case, instead of occurring at 4.2 degrees, happened at 77 degrees. This is high temperature, but it's not conventional. In what sense is not conventional? Non-conventional means not just because of the high temperature. Non-conventional means that the pairing mechanism is not of type S of S1, as I will tell you. Then, in 95, came the discovery was the first realization of the Bose-Einstein condensation in ultracold atoms. And then in 1909, was the first consecution of the degenerate Fermi gas. Then there was another jump of what? The jump crucial is that instead of having just neutral atoms, what the experimentalists reached was a Bose-Einstein condensate composed of fermionic molecules. Then in 2015, a Bose-Einstein condensate in a dipolar gas was observed, and then more recently, a dipolar Fermi molecules in the ground state were realized for the first time. And perhaps the last discovery or the last experiment related with this phenomena is the consecution of the dipolar Fermi molecules confined in a lattice. And this is crucial for the model that I will tell you. Okay? What we can say in a summarized way about superconductivity? To summarize the superconductivity and specifically the contribution of the Bardeen, Cooper, and Schiffer, what we can say is that the phenomenon consists on zero resistivity at this temperature, and then how can we explain that in a metal one can get zero resistivity or zero viscosity in the case of superfluids? So what we do now, but is based in the work done by Bardeen, Cooper, and Schiffer. And it is very simple to see that the specific problem, we know what are the elements of the problems. The elements of the problems are particles having a certain energy, single particles, and particles interacting, but interacting with a special characteristic, that particles interact with opposite spins, having angular momentum 0, and also with a contact interaction. So this Hamiltonian is a Hamiltonian written in the grand canonical ensemble. This is why it appears new here. And then, what was the work made by Bardeen, Cooper, and Schiffer? I think that the essential thing was the work made by Cooper. What Cooper did is to propose the mechanism from which the scattered pairs can be formed. Pairs are not bound. Pairs are still continue having the identity of being fermions. That is, the wave function of this pair of electrons is still a wave function of fermions. And then, so what is important is that Cooper proposed that electrons have an effective attraction as a result of the lattice in which they are confined. This is the proposal of Cooper, and what we see here is the gap. It's the energy gap. The order parameter as a function of the temperature. Remember, as I told you, that the order parameter is a quantity that below the temperature, the transition temperature becomes different of 0 and becomes 0 above the transition temperature. And what it is important to say is that providing an energy above this energy gap to the system, this destroys the superconducting state. The other important thing is that with the Cooper work, doing a variational analysis, this is one of the forms in which one can obtain the quasi-particle energy spectrum and see that instead of the usual parabola, what they have is a parabola shifted, which is this energy spectrum, and this energy spectrum corresponds precisely to the energy spectrum of quasi-particles paired with this mechanism associated to the presence of the lattice. This is in pink. Then, what else? But this was superconductivity and was understood by the Bardeen, Cooper, and Schiffer theory. But what else? As I told you, in 1986 was discovered the high TC superconductivity. And until now, we don't understand how. We know a lot of phenomenological information of high TC superconductivity, of course. But what is unknown is the pairing mechanism of the electrons. This is the unsolved question. Here, in these lines, there is a summary of the known wells. So, it is known that conduction occurs by copper pairs. That is, the conduction is also with pairs of electrons, but we don't know which is the mechanism behind the formation of these Cooper pairs. Under the presence of a magnetic field, what it is observed is the formation of quantized vortex of magnetic flux. The conduction occurs in layers of the copper and oxygen planes, and the size of pairs is of this magnitude. Also, another characteristic phenomenologically known from the high dc superconductivity is that this is of type D wave. Why D wave? I will tell you why D wave. Here in this plot, I'm summarizing so how as the time passes, in several laboratories around the world, they are increasing the critical temperature at which superconductivity has been observed. And see, you can see here the 1986, the superconducting transition in mainly structures forms of yttrium, barium, and copper, and some other substances, of course, as rutenates. I cannot see here. Well, what about superfluidity? And how are related superconductivity, non-conventional superconductivity, and superfluidity? How are related? So remember that, again, you will always see this Hamiltonian is the same Hamiltonian because it's the same system. But superfluidity is a phenomenon that occurs not between electrons, but in neutral particles that interact. It's like a superfluid. So you have particles interacting through which? Through a potential. Here, to explain the superfluidity in helium-4, Bogdan used the fact that superfluidity occurs with a contact interaction between particles that belong to the fluid. Remember that, as I told you, that the superfluid state was found first by Piotr Kapitsa, John Allen, and Dan Meissner in 1937, and then this phenomena was explained by Bogdan for helium-4, the boson. But what happened in this year, in 1971? So superfluidity was realized in the fermionic neutral atoms of helium-3 and then explained by Ley. But remember that here I cannot, so the video cannot work here. What was here is a container. No, I can't glass. Sorry. This is a container in which you can see that the superfluid goes across the walls of the bottle and then goes out because of the superfluidity. Because the superfluid here, that is precisely helium, is in the proper temperature to see the transition. What you can see here is the energy spectrum, analogous to the energy spectrum for the case of electrons, in the case of superconductivity. This is the spectrum of the superfluids. And this is according with the Landau criteria of superfluidity. And of course, this contribution was explained later on by Feynman, which is called the rotonic part of the of the energy spectrum. So, what are the similarities among superfluidity and superconductivity? The similarities are that we have the same Hamiltonian for both systems. This Hamiltonian. And what Bardeen, Cooper, and Schiffer showed us about the solution of this Hamiltonian. What they did was to propose the ground state for this Hamiltonian. Tremendous, right? And the procedure, here is one way of explaining the procedure, is that this interaction term that nobody can live with this, nobody, no one of us, nobody can live with this term. So what they did is to decouple this term of 4 operators. So remember that what this term means, just for the students, what this term means is the collision of 2 particles interacting with momentum k prime and k prime both spin up and spin down, and then so 2 particles interact and collide, and then this particle destroy, and as a result of the collision, 2 new particles having again momentum k and minus k are created. This is the meaning of the collision term, but this is impossible to deal with. So the work of Bardeen-Cooper-Schiffer is precisely to convert this term into a single particle, to kind of single particle term. So this term can be approximately written as the expectation value of this pair plus times this particle operator of one single particle and this other term. But what is this term? This term is precisely related with the energy gap. But remember that the energy gap is crucial in what is the energy spectrum. And the energy spectrum makes the difference, the main difference. But the energy spectrum is related with what is the interaction that allows to form the pairs. And what else? So once that this decoupling is performed, then one again substitute this in this pink square, this expression in the pink square, substitute this in this expression, which is the most general Hamiltonian of either the superfluid and superconductivity phenomena, and then what you obtain is a new Hamiltonian, but a new Hamiltonian with just single particle operators, but not diagonal. This is the bad thing. But when we have something that is not diagonal, what we do is just to perform a transformation, in this case a Bogdan transformation, that takes this Hamiltonian and leads to this other Hamiltonian, which is perfectly diagonal. And what you can read from here is the ground state energy plus the excitation energy of the quasi-particles. So what are these quasi-particles? Well, these quasi-particles are the superposition of, yes?
What are the excitation relations between?
Of fermionic, of course. Yes. Very good question.
And you can do a Bogdan transformation.
Yes, because when you have fermions, you impose a computation relation for fermions, and when you have bosons, you impose a Bogdan relation for bosons. You respect that, and then you obtain different normalization conditions. But the main ingredient is to see that, so this is the most important quantity, and this quantity, the energy gap, brings the whole information of the interaction, that is, which is the process that allows to pair the particles having momentum k and minus k and spin sigma and sigma prime. And what is the meaning of Bogdan transformation? By doing the Bogdan transformation allows to have this equation in general. This equation is when we have contact interaction. But what happens when we don't have contact interactions? When we have long-range interactions, then instead of this quantity U, so B is the volume, but this quantity U represents the amplitude of the interaction. So instead of this quantity U, when you have non-contact interaction but long-range interaction, this equation is replaced by this other equation in the red square. And this is our important equation. What you can see here is that the energy gap is related with what is the interaction between the particles, and of course here there appears the temperature and the energy spectrum. And this is obtained just from the volume transformation course.
So capital B
Yes?
how is defined capital B? When you have minus you all
Yeah. Capital B is the volume again. Yeah. This is exactly the same equation, but this is for the case when interactions are non-contact interaction, but long-range interaction. And this is the important thing in the analysis of the superfluid, of the non-conventional superfluidity.
so contact interactions do not depend on capital.
Yes, exactly. And this is precisely what I will tell you right now. The energy gap, as I told you, still must be antisymmetric, because they remember that they conserve the identity of being fermions, because they are always fermions. They are not paired as bound molecules. They are scalar particles and the whole. So in my mind, the BCS state is the superposition of this state and this state and this state and this whole pairs. What it is illustrated here is of what kind can be this energy gap. So must be antisymmetric, and this can be antisymmetric if and only if the spatial part times the spinorial part becomes antisymmetric. But the spatial part can be, so this is the spinorial part when it's S equals 0, which is this one. And in this case, the angular momentum must be 0, which is the S wave, because this is antisymmetric and then this is symmetric, and then the product becomes antisymmetric. This is a conventional superconductivity case. It is expected that this is the non-conventional superconductivity case, because phenomenologically it has been shown that indeed the non-conventional superconductivity is of this type. But what happened when S equal to 1? Then you have just symmetric state, and in this case, in order to guarantee that this energy gap is antisymmetric, what you have to impose is that the spatial part must be antisymmetric. That is, L equal 1 or L equal 3. L equal 1 calls P wave, and L equal 3 calls F wave. We shall concentrate in L equal 1, that is P wave. But this is related with non-conventional superconductivity. And how at the beginning I mentioned that what we did is to propose a model to study the non-conventional superconductivity. Our model is based on the use of ultracold atoms. Okay? How? So what are ultracold atoms? Ultracold atoms are a huge collection or microscopic collection of neutral atoms. So the first time that Bose-Einstein condensation was realized was in atoms of this kind: lithium, sodium, potassium, and rubidium. So this macroscopic collection of neutral atoms in its low energy state are obtained by means of laser cooling procedure and evaporative cooling procedure. With these procedures, the sample reaches this temperature, and in the laboratory what they get is samples of with this density, so they are very dilute gases, are 5 times 1,000, no, 5 tens, I don't know. No, I better not to mention that. So those gases are very diluted in the laboratory. This density is really, really small, okay? And why is really small? Because in this case, we can neglect collisions with 3-body or 4-body and so on. Since they are diluted, we just have to consider 2-body collisions. And another feature that is important to say is that this experiment always occurs in a harmonic environment. They do not occur in a homogeneous space, but instead of that, in a harmonic environment. And this harmonic environment, of course, is related with the form in which the atoms are confined. Now, let me tell you that in October of last year, in the Inst.Física, the Bose-Einstein condensate was realized for the first time. This is the group that observed for the first time the Bose-Einstein condensation here in Mexico at UNAM. What they observed, what they did in their laboratory was a Bose-Einstein condensate composed of lithium molecules interacting through a flashback resonance. It's a peculiar, it's another topic, sorry. But what they did is a Bose-Einstein condensate I remember it at these temperatures. So they obtained around 80,000 of particles. How we can use these ultra-cold atomic gases to study or to understand superfluidity. So, of course, I am a theoretical person. I'm not an experimentalist, but what I do is to use the models based in the ultra-cold atoms and then to propose the study of superfluid state, for instance. Why these ultra-cold atoms are called quantum simulators? Because what you can see is that you can manage in a laboratory, they can manage the kinetic energy as well as the standard potential where the neutral atoms live. They can also manage the dimensionality, and also they can, as I'll show you in the next slide, they can confine the neutral atoms. The neutral atoms are these circles, these balls in red. So the neutral atoms can be confined in these optical lattices. The optical lattices form as a superposition of two laser light, and as a result, a standing wave is formed like this one in the one dimension. And these are cartoons showing how ultra-cold neutral atoms can be confined in different geometries of ultra-cold lattices, which are called artificial crystals of light, can be formed as a superposition of several arrays of lasers. Okay, and what else? So, but even more, besides controlling the dimensionality and the structure, the spatial structure where the atoms live, but another thing that can be controlled is the interatomic interactions between particles. The interatomic interactions can be controlled externally by means of flashback resonances, and I think, of course, the book of Landau is a very good book in which an excellent summary of low energy collision can be studied to understand why the scattering length is the main parameter that is the effective parameter that represents the amplitude of the collision. So, since in the laboratory they can control the interactions and the dimensionality, the result is that the atoms, neutral atoms, are kind of electrons traveling in a lattice. But this lattice is not formed by the cores of the nuclei, but this lattice is formed by light. And this is our starting point to propose our model. But before saying what is our model, just let me use 2 slides to tell you that why we propose this model, because there are experimental work done in 2015 in which what they did is to observe the ground state, the vibrational ground state of dipolar Fermi molecules for a long time. What is long time? 2.5 seconds. But 2.5 seconds is a huge time to make experiments. And even more, what they can do is to control the effective interaction between dipoles, cooled at this temperature. Why control the effective interaction? Because by means of an external electric field, they can control what is the effective dipole moment between the dipole moments. So the effective dipolar interaction is given by this. Then, why are so important these dipole-dipole interactions? Because dipole-dipole interactions, since they are long range, they can form different phases in matter. As for instance, they can form, super solid phases, they can form stripe phases, and here I'm just plotting a couple of works. This is our model. Our model to study non-conventional superfluidity consists in a bilayer in which we confine fermionic molecules of the same type, but pointing in opposite directions. And although it is not realized now in a laboratory, we think that with the present infrastructure it can be reached. So our model then is this. So a bilayer formed by light, as I told you, in 2 dimensions. Then Fermi molecules sitting along the sides of these 2 layers. I will call layer E and B, A and B. And A is the size of the lattice. So the potential energy between Fermi molecules of green type and blue type is given by this expression. L is the separation of between layers, and R is the distance in the plane. So is the intralayer distance. What is chi? Chi here is related with the effective interaction of molecules of this type and this type. And remember that this effective interaction can be tuned by means of an external electric field. So the problem that we have is exactly looks like the Hamiltonian that I wrote before. That is a Hamiltonian having kinetic energy. Also, since it is written in the grand canonical ensemble, this is why you can see here the chemical potential. And the other part is the interacting one, written in the momentum space, of course. And what you can see here is the Fourier transform of this interaction potential. This omega is the size. Remember that you have the volume in the 3D case, and now in this 2D case you have this omega, which is the area of these lattices of our example. And so what we will do is to study which are the states arising from this Hamiltonian, given the fact that we have this potential energy between Fermi molecules of green type and blue type. But first, as I told you, we studied the two-body problem. The two-body problem in one dimension for simplicity. And the two-body problem consists in solving so we proceed exactly in the same way as Cooper did, and then we find the binding energy. So you can see that here I'm plotting the absolute value of the binding energy, this EV, and what you can see here, what is chi? So remember that chi is proportional to D, and D is the effective interaction that can be varied as a function of an external field. So the problem to be solved then depends, of course, on the value of chi. So this is just the two-body problem. When you solve the two-body problem, what you can see is that for values of chi lower than 0.5, you can have scattered state, and for values of chi above 0.5, what you have is bound states. That is, for all of these values of chi, you have just bound state. But remember that the superconductivity is composed of non-bound molecules, not binding molecules, but scattered molecules, in order to form the Cooper pairs, in this case. So what you can see here is the exact solution, and that is the exact diagonalization of the Schrödinger equation for the scattered states for a value of k equal to 0.4, of course lower than 0.5, and this is the energy, and this is shifted. So this energy indeed is negative, but we shifted this energy just to show in a plot the whole energy spectrum. And what you can see here is there are a little set of configurations of energies associated to the highest possible energy. Why the highest possible energy? So the highest possible energy is when one green arrow is exactly on top of the blue arrow. Why? Because since they have opposite dipole moments, they repel each other when they are at the same site. But if you adjust this separation, then an effective attractive interaction can be established between these Fermi molecules and these Fermi molecules. But whenever the Fermi molecules are not seated each on top of the other, when they are in other sites, they can have an effective attractive interaction. And this is our mechanism that we propose as a Cooper mechanism. This is the attractive mechanism in this guy, in this experiment, in this model. And this is a summary of the two-body problem in one dimension. So remember then that what we have to explore, what we have to consider in our many-body problem based in the result of this two-body problem is values of k lower than 0.5. Why? Because in this inset, what I am showing is what is the probability of finding a Fermi molecule situated a distance r from the other. Distance r, remember that is the intraplane distance. And what is the bigger plot? In the bigger plot, yes.
This probability or the histogram of the probabilities?
The histogram of the probabilities, you're right. Yes. And what you can see in this larger plot is the probability for a value of chi, I think is 1.8. So what you can see here is that the probability is enormous at r equal non-zero, but then the next. But this for a value of chi very large. So this is, as I told you, a summary of the two-body problem. And what happened with the many-body problem? Again, we...
Can I make a stupid question?
No, it's
Can
not
we
stupid.
go back?
Yes.
I may not understand why
Uh-huh.
the lattices are dropping up and down at the bottoms. I would expect, like, for example, up will be attracted to peaks, and maybe that's just a misunderstanding.
So the model is someone put the molecules, so you have the optical lattice in two dimensions.
Yeah.
Then by another mechanism
Okay.
you can
Perfect.
find.
Okay.
Okay.
Yeah. Thank you.
I'm not explaining the mechanism.
Exactly. Yeah,
last.
yeah. Thank you.
Of course.
Yeah.
Okay. So what happened with the many-body problem? So to deal with the many-body problem, we again consider the BCS theory, but now with the consideration that the energy gap is, as I told you several slides ago, of this, this kind, is related with the interaction potential that forms responsible of forming the pairing. Okay. So when you do the algebra of proposing this decoupling as the same as I explained before, I mean the decoupling of the two particle of the two-body term, then what you have to solve is this coupled equation, and this coupled equation depends on n and on chi. Remember that chi is enclosed here. Chi is the effective interaction. Thank you. I'm finished. And what is n? N is the density of particles in the lattice. I mean the filling factor. So what you have to solve is these two effective equations for the system. And remember that these two effective equations, I mean the equation for the energy gap related with the interaction, and the equation for the filling factor, of course, is related with the filling factor because remember that the energy gap is indeed inserted between this energy. And then when you solve this equation, what you obtain is that this kind of solution. And this kind of solution is exactly P-wave solution. Why? Because it looks like a sine function. So what you can see here is the real in the solid line and the imaginary part of the energy gap as a function of k in the first Brillouin zone. And then, remember that what you have is kx and ky, and what we did is kj equal to 0 here, and then we show just a cut. And of course here what we see here is a cut in the other direction. And also you can see the same structure, that is, substituting this kind of potential supports P-wave states, superfluidity in P-wave states. And what else? Well, I will show you, and I will finish with this, the next two slides, is that here you can see a kind of phase diagram of the chemical potential as a function of the filling factor. So remember your class your elementary class of this when we studied the van der Waals phase diagram. So remember that what we have is this energy Maxwell equal areas, the construction of Maxwell of equal areas. And remember that in this construction, what allows to recognize is that the parts which are prohibited because of the second law of thermodynamics, this part is all prohibited because in this case the compressibility is negative and this cannot be, and this is why this part does not exist. But what happened? Then when the system acquires the chemical potential of this value, then what happens is that the system separates into different superfluids of different densities, exactly as the van der Waals equation of a state. Then what we see here is a superfluid having P-wave superfluidity, but breaking in two phases with two different densities. What else? So finally, in this phase diagram, I want to summarize two things. So here, what I am showing you is the chemical potential, the same as the previous transparency. The chemical potential as a function of n for different values of chi. So this curve corresponds to different values of chi, and this is the construction of equal areas of Maxwell, exactly the same way as before. And here, this diagram summarizes the whole regions in which you can see the superfluid phase with two different densities. What it means is that for this value of K, the system breaks into a phase having this density and another part having this density. With this, I want to finish because, of course, it's a large story, but what is still the other important part is that this phase transition is not the standard phase transition, but is of type BKD, the Berezinski-Kosterlitz phase transition. Why? Because this occurs in a 2D system, and in this kind the transition is not the standard transition, but is of type BKT. This is another story. And then here I want to just summarize with some lines the conclusion of our work. So with our model, we were able to observe P-wave superfluidity. I mean that the proposition of this potential interaction supports this kind of superfluidity, type P-wave. The model consists of dipolar Fermi gas situated in a square lattice in 2 dimensions. So first we studied the physics of two-body, and then with the parameters that we obtained from the physics of two-body, I mean the binding molecules and the scattered molecules, then we analyze the possible Cooper pairing with in the many-body system, and we use the BCS theory. In particular, we studied the behavior of the other parameter, and from this study, what we observed exactly was the emergence of P-wave superfluidity. Because, as I showed you, the antisymmetry, I mean the sign function, is exhibited in this order parameter. Finally, I show you the phase diagram which show the phase separation into different densities. And thank you very much.
We have time for questions, so please.
I have questions actually. I really liked it because I have a stupid question again. Because in an experiment you can just get to one of these current states, right?
Yes.
And so let's say that we have a long-range order correlation between the pairs, right?
Exactly.
But actually in the experiment you could move one of the lattices to bring them
Yes.
to short order.
Yes.
And so you could actually try to go for this BCS
Exactly.
crossover of things?
It's a very good question, Blas. It's a
should it
really
be
good question.
possible?
Why?
Stupid,
Yes.
but good.
No, it's indeed a very good question. Because I didn't tell you that it's very important, the distance of separation between molecules. Because if you have a long separation, what you have, you lost completely this attractive part. And then you lost this big wave formation, superfluidity. And it depends exactly. So, of course, Blas, it's a very good question. So, for certain values of this L, this potential becomes non-attractive but repulsive.
Repulsive, exactly.
Yes, and then you don't have Cooper pairs anymore. And then this is why to fix this distance is an essential feature to observe the emergence of P-wave superfluidity.
And actually, I was thinking more on the transversal side too, because when you get a ground state, you get the localized pairs, even
Yes.
short or long range, and you could in the transversal plane you could play erratically with the
Sure.
range distance. I think.
You can also have, indeed, you can also have interactions between particles between green and green. Indeed.
Okay. Okay.
But we are neglecting such interactions because compared with interactions
Yeah,
between
yeah.
difference are
And stronger. Yeah.
stronger. Right, yes. Thank you.
Thank you.
Okay, now another question.
In the first part of your talk, you tell us that there is an immense connection between superconductivity and superfluidity.
Yes.
And I understood that all the preeminent part of your talk was addressed in that direction.
Yes, exactly.
Well, did you point out that superconductivity is intimately connected with quantum field theory? Indeed, one can make some translation from superconductivity to quantum field theory and vice versa.
Mm.
Is it possible to make this kind of connection between superfluidity and quantum field theory also?
Indeed. Indeed. I didn't told you about that, but with my student, Arturo Camacho Guardian, so who did his PhD working with me, we use field theory to address the problem of supersolid phases. Of course, are the same mathematics. You can also deal with superconductivity or superfluidity phenomena.
Yes, because this connection is the two pictures.
Yes.
Very big. So that if you know very well quantum field theory,
Yeah.
you can make the translation and do also
Sure.
in the case of superconductivity, well, that. But now
Yes, exactly.
it is also superfluidity.
Sure.
Do we have another question?
You mentioned this cluster is solid phase transitions
Yes.
in the 2 layers.
Yes.
So I think you have one such transition in one of the layer,
Yes.
another gating transitions in the other layer, and how these type of phase transitions are connected with the superfluidity.
Okay. Yes, I will show you one transparency to answer your question. So,
You were not already.
before the talk, we talk. No. So, as Mielnik-Manwelow theorem establishes, in dimensions less or equal to with a continuous field, there cannot exist long-range order at finite temperature. And this is connected with the BKT transition. And these systems, for instance, are magnetic systems. Heisenberg, the XY model, in which we have a continuous field. I mean, the spin has every value. And in the other side, there are this transition in the case of superfluid films of helium. What is the important thing, or what is the essential thing for which they are indeed a BKT transition. Although they are no longer a usual transition, but they are a second order phase transition because the correlation behaves like this in both cases. Then, in thin films of helium, you can see this kind of transition. This is why in our system, because of being a superfluid and being confined in 2 dimensions, the transition cannot be the usual one, but must be of BKT. And then what we use is the sorry. Lo perdí. In our case,
So BKT, it's not exactly KTP, what does it mean?
Brzezinski, Kosterlitz, and Fabre's transition. And what we use just to recognize what is the temperature that we can predict from our model is just to use the well-known relation for the BKT transition, which relates the superfluid density with the temperature. And this plot is for our model, and this curve is this dash line corresponds to this equation, and the intersection with our model gives the transition at which can be observed the temperature. Can be observed the transition to the superfluid P wave of type P
Okay,
wave.
so you have this rho over T here,
Yes.
which is parabolic. No, rho over T.
The y-axis.
And you just intersect with the linear formula for
Yes.
rho in the case of BKT.
Yes, exactly. And this is our prediction. Yeah, well, I want to mention that in any laboratory, nobody can observe these temperatures. This is the bad thing of our model. So this is unreachable temperature with the current structure, infrastructure in any laboratory in the world. Not in Mexico, not in anyone, not in any place.
Okay, well, we don't have more time. If you have more questions, please use the coffee break for that. On behalf of Quantum Bar, let me thank for this presentation.
Thank you very much.